Today, we'll be talking about steps to determine if a factor is significant. Please don't forget to share our link and click on subscribe button. If you have significant results, it means that your result likely did not happen by chance, that is due to the change in the level of the factors. If your result is insignificant, you can't reject the null hypothesis. So in this lecture, we want to show you the steps that you can take to determine significance of your results. The first one is for you to determine the sum of square. This sum of square measures how far individual measurements are from the mean. To calculate the sum of square, you subtract each measurement from the mean, square the difference, and sum up all the resulting measurements. Mathematically, we say that SS, which is sum of square, is the summation of small x minus capital S all squared. Small s is the individual data, while capital square is the mean of the data. In ANOVA, total sum of square is the sum of the within sample sum of square, which is your error, and between sample sum of square, which is your treatment. So mathematically, is SST is equal to SSE plus SSF. SST is total sum of square. SSE is error sum of square. We can say is within sample sum of square. SSF is factor effect sum of square or between sample sum of square. The calculations is more tedious when done manually, so statistical software can be used for the calculations. You still remember that the formula for calculation of sum of square differs depending on the number of factors involved and if replication is also involved. So the second one is the degree of freedom. Degree of freedom is the amount of value within a sample that is free to vary. It equals your sample size minus the number of parameters, that is your response you need to calculate during the analysis. So mathematically, df is equal to n minus 1. So to demonstrate this, let us say that we are told to pick a set of numbers that have a mean average of 10. So you have these three options. You have option A, 9, 10, 11. Option B, 8, 10, 12. Option C, 5, 10, 15. So on each option, if you total it and find the mean, they are all 10. So determine the third value from this if you decide to pick two of this and want to calculate the third value. So to determine the third value, you must choose first two values. So either you choose 9 and 10, or 8 and 10, or 5 and 10, from which the last one can be gotten from the mean. So therefore, only two values are free to be manipulated in this example. If you choose 9 and 10, 8 and 10, 5, you can get only the third one by calculating the average or the mean. So in this case, you can say that the difference, the df of this equation is 2. That 3 minus 1 is equals to 2. So for ANOVA calculation, depending on number of factors, we have this degree of freedom. For two factors of A and B, with the interaction, we have SSB, that degree of freedom is LB minus 1. For SSA, that's for factor A, the degree of freedom is LA minus 1. For SSAB, the interaction of A and B, the degree of freedom is LA minus 1 into LB minus 1. Then if you have three factors without replication, we have SSB, degree of freedom is LB minus 1. SSA, degree of freedom is LA minus 1. SSC, degree of freedom is LC minus 1. Then SSAB, that interaction of A and B, degree of freedom is LA minus 1 into LB minus 1. SSAC, degree of freedom is LA minus 1 into LC minus 1. SSBC, degree of freedom is LB minus 1 into LC minus 1. Then SS, interaction of three of them, ABC, degree of freedom is LA minus 1 into LB minus 1 into LC minus 1. Where LA is number of levels for factor A, LB is number of levels for factor B, and LC is number of levels for factor C. Then the third factor is the mean square, MS. This means this MS is the estimate of the population variance based on the variability among a given set of measures. It can be calculated by dividing the sum of square by the degree of freedom. That mathematically, you can say that MS is equal to SS over DF. The fourth one is F value. As we have discussed earlier, F statistic can be used when deciding to support or reject the null hypothesis. In your F test results, you will have both F value and F critical value. This F critical value is also called F statistics. So the value you calculate from your data is called F value. That's the one without critical part. So it's not appropriate to take decision on your result based on F value only. It is more appropriate to judge your significance with P value too. You don't reject your null hypothesis only if your critical value is smaller than your F value, but only when your F value is small. So say have if the F table is collection of tables for 4 alpha levels, we have 0 0.1, 0 0.5, we have 0 0.025, we have 0 0.01. The fifth one is the alpha level. Alpha levels are controlled by the researcher and are related to confidence levels. You get an alpha level by subtracting your confidence level from 100%. So alpha levels are like the amount of risk you can take. Example, if you want to be 98% confident in your research, the alpha level will be 2%. That is 100 minus 98, 2%. When you run the hypothesis test, the test will give you a value of P. So compare that value to your choosing alpha level to give verdicts concerning your result. So assuming you have a P value of less than 0.05 and your alpha level is 5%, it means you have a strong evidence that you have 95% confidence to reject your null hypothesis, though it still leaves you with like 5% risk. That noise is a culprit. But if 5% is too much for you, you can decide to set a standard, reduce it to 1%, ensure that you have 99% confidence level. You can equally decide to take the higher risk by taking 10% risk, that being 90% confidence. Then the sixth one is your p-value. P-value is the probability that your result could have happened by chance. It indicates that the null hypothesis is true given a sample data. They gauge how consistent your sample statistics are with the null hypothesis. So specifically, if the null hypothesis is correct, what is the probability of obtaining an effect at least as large as the one in your sample? So first, your p-value calculation assume that the null hypothesis is correct. Thus, from the p-value point of view, the null hypothesis is 100% true. P-value assume that the null is true and the observed sample effect is caused by random sample error. So, as the p-value increases, it means that the null is true, that the probability of the high effect occurring by chance is high. P-value are expressed as decimal, although it can be easier to understand what they are if you convert them to a percentage. Example, a p-value of 0.0254 is 2.54%. This means there is a 2.54% chance your result could be by random error, that it can happen by chance. This is pretty tiny though. On the other hand, a large p-value of 0.9, that is 90%, means your results have a 90% probability of being completely happened by chance and not due to anything in your experiment. Therefore, the smaller the p-value, the more important, significant your result is. This p-value can be obtained from any statistical textbook. Thank you.